Yeah, so then welcome to the plain algebraic curves class. So I'm Andreas Gathmann, for those who don't know me. And I'll have this class together with Cedric Brendel. Probably you know them already. And so these are our coordinates, like the email address and the office number, and that's Cedric's email address. So Cedric is not here for this and the next week, but I think still he's, oh, okay, so good decision. So he will be here from the starting from the third week, which is okay because that's when we start with the example classes. So the most important digital resources will probably be like the OLAT course that you've probably found, or alternatively like the web page, the same content, so the one or the other, where you'll find like all the stuff for this class, whether it be the homework or the class notes or the video recordings or everything. And you can find it on both parts here. And then we have this system to like the URM system for the example classes. It's not that important for our class because there will be only one example class anyway, which is on Fridays at 11:45. I hope is that okay for everybody? Well, obviously, I mean, there's not enough people here to have more than one of these example classes. So, but still, it would be nice if you could register there because that's the system where that will print the certificates at the end. So it's good if you register there if you want to have one. So that's until Friday noon. So just click that it's okay for you. You have to do that from the university network or VPN from anywhere else. And that will shut down again next week. So that's just like for this week. And this is where all the information is for the rest of the semester. So then the class will just be like, so is that time here also okay for everybody? Because I guess this is small enough that if not, we could change it. Okay. So that will be then here like 1:45 on Mondays. And additionally, we have these example classes. They are like every other week, bi-weekly. We have both the homework that starts next week. So I'll just put this on the web page just after class. So on Mondays, anytime on Mondays, whenever I'm done with that. And you would have like 8 days to do that. So like the submission date is Tuesday, the day after, the week after. And we start with that next week. So April 24 today, there will not be enough to do that actually to have an example sheet. And you can submit it as you like, either on paper or online. So that means if you do it on paper, there are some mailboxes downstairs at the entry next to 48-210, and or in the OLAT course, you will find a submission tab. So then if you have a PDF file, you could just submit it there. You can do it in groups of up to 3, which means, if you want to. So, there's not that many submissions probably. But that's okay. For the actual credit afterwards, you'll need an oral exam anyway. So this is just more like in case you need the certificate. Yeah, so that's the example class. I told about that already. And for the certificate itself, so for this Schein, as we call it, like in German, you need to just take part in these example classes. So they will start, by the way, they start in the third week. So we have like the odd semester weeks for our classes, and there's no example classes this week, so it starts May 5th, Friday in the third week of the semester. And there we could discuss already like the first homework set that the next week on Monday. And so for the certificate, you will take part in that, and you want to have at least 70% of the homework problems with at least 1 out of 4 points. And that's not very much, but that's enough for that. So for the final credits for the bachelor, you'll need probably an oral examination. Yes, so I told you already all the information will be in this course, so on that web page, and in particular that includes class notes. So just about the state of the class notes, it's now the 3rd time that I'm teaching the class like that, and from the first to the second time there were quite substantial changes. So I would expect that now from the 2nd to the 3rd, there are minor changes in the class notes, but there will still be changes. So I guess it's okay if you want to have a look at notes either before or during class. You could use the old ones, which you can find in the OLAT course, but I'll update them as the semester goes on and then put the updated notes there. Also, as you see, so we'll have video recordings. I think, students wanted to have that. So I guess if you want to have it afterwards, so you cannot come for a week or so, you'll find this also on the course. Afterwards, that usually takes a while, so probably like the day after, because like post-processing takes some time, but then you can find it there. Also like the homework, and whenever we have something that we want to email you, there's this news tab in the OLAT course, so that activate so that you get the emails. And there's also, if you want a discussion forum, an online discussion forum. Actually, if you have any question, you could just ask me. I mean, either come to my office or just ask after class or whenever you feel like it. And I guess with Cedric, it's pretty much the same. So he doesn't have an office, but I mean, you can email him pretty much always on Discord, it seems. He's also in the student council, so maybe you find him there in the office. Yeah, so that's about the organization of the class. So is there like any questions about that? Right. So then let's talk about maybe what the class is about. So what's the motivation about the whole thing and what's plane algebraic curves? So in case you don't know, so this class is meant to be the introduction to the algebraic geometry specialization. So it's sort of a light introduction to algebraic geometry. And so that is meant to be attended by people who haven't essentially attended anything except like the algebraic structures and the foundations of mathematics. So we'll not assume any commutative algebra in particular, although, I mean, of course, that is important for algebraic geometry. Maybe I could just ask, I mean, how many have you attended, or have some of you already attended commutative algebra or not? Who did that already? Like you? You don't? And you don't. Okay. So I can every now and then just give you some relations to that. So have you had a commutative algebra class? I think we talked about that already, sort of, right? Yeah. So I mean, there is some relation to that. I'll talk about relations to other fields of mathematics anyway. So in particular, this curves class, I mean, there's so many relations to other fields of mathematics that I cannot really expect that you know this all. And so I'll just do it every now and then for fun, basically, but will not be assuming that. Well, what is algebraic geometry, after all? So it's, in a sense, a combination of linear algebra and algebra. Namely, what you do is, so what is linear algebra? The blackboard. So of course, you know, like linear algebra, what you usually do, or the main topic, or one of the main topics, is that you consider systems of linear equations in several variables over a ground field. In several variables. Over ground field. And then there's also the algebra, in the sense that would be our introduction to algebra class, where you usually consider, well, not systems, but one equation, or one thing that you consider is a polynomial equation in one variable. That's one part, like that you consider like solvability of polynomial equations or something like that over a ground field. So in algebra, standard algebra, you would usually consider, or one thing that you consider is polynomial equations in one variable over a ground field K. And what algebraic geometry does, it combines those two, and you consider several polynomial equations, well, in several variables over a ground field, and then study that, right? So in that sense, it's a combination of those two. And what algebraic geometry does is consider several polynomial equations in several variables. Again, over a ground field. And in this class here, so that is meant to be a gentle introduction, in the sense that we'll consider the simplest possible case that you could have, namely you have a one polynomial equation in two variables. So in this class, we consider the simple case. Well, it's not that simple that we couldn't talk about it for a semester, but I mean, compared to all of algebraic geometry, it's simple in that sense. Namely, we consider one polynomial equation in two variables. And of course, if you have two variables, then you're sort of in the plane. And if you have one equation and you draw it, you expect it to be a curve, and that's why it's called plane. So that will lead to plane curves. So hence the name of this class. And maybe we could just, in this motivational part, I'll show you a few examples, namely showing how many relations this actually has to other fields of mathematics, because that's quite a lot. I guess you probably know or would expect that there's relations to commutative algebra, because, well, I mean, after all, you consider polynomials, polynomial rings are somehow a big topic in commutative algebra, and you study a lot about that. So, yes, commutative algebra is sort of like the algebraic part of algebraic geometry, and the geometric part is a little bit what we do here. And maybe more going into other regions of mathematics. And so, of course, that's like the main thing. And if you want to actually compute stuff, like it goes into computer algebra, what we also do here, like, of course, doing here at the university, then if you do it over, depending like which field you work over, so if you do it like on number fields or finite fields, you go like into number theory or into cryptography even, or you could, if you're more into like the real or complex numbers, you're thinking about the topology of these things, so it goes like into, like for example, into topology or complex analysis if you're a complex number. So basically polynomials occur everywhere in mathematics. It's like such a simple structure that pretty much anything will lead to polynomials. And I'll sketch these relations to these other fields of mathematics, as I said, like every now and then, but I don't want to assume anything except like a basic knowledge of rings, essentially. So if you know what a ring is and have seen a polynomial ring, that should be fine. So whenever I need something really from commutative algebra that we have to assume, I'll just mark it like as a fact and then say, so this is a fact and we just believe this. Right? In fact, from my experience, like when I taught this class before, I found that most people like this class even better if they don't know commutative algebra, because if you do, well, sorry, but I mean, because if you do, you probably every now and then have the feeling, well, yeah, what can't you do it properly? You know, I mean, because there's like actually some commutative algebra behind, which I try to hide somehow because I don't want to assume it. But if I know, like, if there's about half of you knowing that, then I can always like mention, so in commutative algebra, it would be that, and it's just a theorem which we are now doing with basic methods essentially. Anyway. So yeah, some examples. So the question is, of course, I said just we study polynomial equations in two variables. So the question is, what do we do with them, right? I mean, so what are the questions that we want to ask about this? And as usual, as you might probably already expect, the goal is not, I mean, this is pure mathematics, so the goal is not to solve these equations. I mean to give the exact solutions. Just because you probably know from algebra, I mean, there is no explicit solution formula even for polynomials in one variable. So that doesn't get better here. So I mean, this is not the point. So the point is just about the general structure of this thing. So like about the geometry, like if you draw these things, what do they look like? And so some questions that you could consider there, I have here in a couple of examples, and they depend actually very much on the ground field. So, I mean, as in linear algebra, you could set the theory over an arbitrary ground field, but depending on what that field is, the flavor of these objects is quite different. So I can show you some examples of that online as well. And here I have to start the yeah. So probably the first, or maybe not the first, but usually the first thing as a ground field you might think of would be the real numbers. And while it should appear in in a couple of seconds. So if you consider one polynomial equation and two variables over the real numbers, then you could just actually draw pictures of these things in the plane. And that would be examples here. It's darker. So these are some obvious examples. So that would be like, so usually call the variables x and y. So this would be just an ellipse. So you have a picture like that. Like a nice curve. Then here, this like x squared minus y squared equals 0. So there you could see already features that we want to study maybe. So that's like x plus y times x minus y means that it's a union of two things that would be curves themselves. So we will later call them reducible in the sense that they consist of two components that are curves themselves. Then this would be like y squared minus x cubed would look like that. So again, this is doesn't consist of two components, but you see there's somehow a special point in the middle where it doesn't look smooth, sort of. So that will be called a singular point. So that will be a singular point as well. So we'll study that, whether a curve has singular points or not. So this one does not, this one has in the middle. And that would be like a curve, an equation of degree 3. Just an example, y squared is plus x minus x cubed equals 0. So that would look like this. And over these real numbers, this picture would have two, well, in the topology sense, it has two components, but actually not in the sense here. So there's already something happening. And if you only consider this one oval here, sort of this one part of the curve, then this would not be the zero locus of a polynomial by itself, only if you take it together with that one. So that would be examples over real curves. So we'll see them later in the class, of course, and that's probably what you would expect curves to look like. So that's over the reals. If we go maybe to the complex numbers, which, well, if you had like a commutative algebra class, might already sound like the more natural choice because it's directly closed in a nicer field. Let's take the same equation that we just had in the last example, right? So y squared plus x minus x cubed equals 0, and ask what does that look like in the sense, I mean, how you could draw it. And well, over C, of course, that means that is a curve. So that means you could, well, essentially you could even solve this equation. If you had a value of x, you could find y from that. So that means it's a one-dimensional complex thing. But that means it's a real two-dimensional thing. And if you draw it somehow, you would expect a surface instead of a curve, right? I mean, it's still called a curve, but it's a complex curve. So if you draw it, it would be a surface. And what would it look like? Well, let's just put it here. So what our equation is y squared equal, what is it, y cubed minus x. And you could factor this, of course, into x plus 1, x minus 1x. And that means you could, as I said, essentially solve it. So that means you could, the equation tells you could take anything for x, and then you have exactly two values for y. Namely the two possible roots, except for the points at 0, 1, and minus 1. There you have only one value. So that means one might think that the curve, if you draw it like topologically, looks like it's two planes, so two x planes sort of, because you have two choices of y for each, except that for 1 and minus 1 and 0, you have only one value. So it might think it looks like, well, it's an x plane here for the one value of y, and x plane here for another value of y. And then they're somehow glued at 3 points where you have only one. But that's not true. I mean, set theoretically it would be true, but topologically it's not true. And the reason why, so that's already starting with these pictures. So here are the 3 points, minus 1, 0, and 1. The reason is that these complex roots, as you know, are not, I mean, there's no distinguished positive and negative root, but rather you would get the root of a complex number, it's like in polar coordinates, by taking 1/2 of the angle and then the square root of the absolute value, which means that if you take, so the function, essentially there's no well-defined square root function, as you know in complex analysis, but if you take, say, x going around the origin in the complex plane once, like, so that means you consider an x of the form, say, some radius times e to the I phi, and phi runs from 0 to 2 pi, then somehow the square root of x would be square root of r and then e to the I phi over 2. And that means if you go around here the circle once from 0 to 2 pi, then here like your square root goes to minus the square root. And so that's just a complex numbers phenomenon. And what that means is in that picture, if you go around such a point where the root is 0, you actually go to the other sheet here. And only after going twice, you're back at the original one. And so that means the correct picture would be, you cut this open here, like here and there. So you still have two planes, but cut it open and then glue it in such a way, as indicated here on the right, that when you start here on the upper plane and go around once here, then you land on the lower plane and go around the lower plane and then again go around the upper plane. And so that means it's rather a picture like this here and not a picture like that. So that means this here would be a topologically correct picture of the corresponding complex curve, which is what? Sorry? Yeah. Well, because if you go from 0 to 2 pi, then here this goes from r square r to the e to the whatever I 0 to the 2 to well, depends on where you go to, but then like pi over 2 only runs from 0 to pi, right? And that means like what you have here as the angle in the square root only makes half of the circle and not the complete circle. And half of the circle, like e to the minus I pi or e to the I pi is just a minus 1. So that means you go to the other, you just switch to the other one. Like, so over the real numbers, you have a unique, I mean, it's a positive root and a negative root. But I mean, in the complex numbers, there's just two roots where you couldn't say which one is better than the other. And then if you go around with the original x, like around the 0, around the origin, then the square root will switch from the one to the other. And that's why you have to make this plane switching here from that side to the other. So once you go around here, you actually land on the lower one and then go up and then you go on the upper one again. And you have to do this in all three cases. I mean, this is not meant to be a proof, right? We're in a motivational section. So there will be proofs of statements like that in the class later on. So that will be a correct picture of it. And actually, as in many fields or topological fields of mathematics, it's always nicer to deal with compact objects instead of non-compact objects. So, I mean, as you might have already like considered, like as for the real numbers, maybe sometimes you want to add a point infinity as limit for something or minus infinity, and the complex numbers, you sometimes have a point infinity. There's a somewhat canonical way to compactify such curve by adding a point at infinity, which makes this thing compact out there and would lead to a picture like that. So again, we'll do this in class. It's just the motivational part. And then topologically, this thing looks like that, which would be a torus. Again, that's as I see. I mean, it's some magic. We'll do this in a couple of weeks. So that should just show you, I mean, that the very same equation that we have, just depending on whether we consider it over the real or over the complex numbers, has a totally different picture when you draw it. So one is this thing with the two parts, with the two components, and this would be a torus. So we'll have results like that in class, what curves look like over various fields. Of course, there's more fields than the real and the complex numbers. So what about finite fields? So that's the same curve, like the same equation, y squared plus x minus x cubed over finite fields. So I just took like z over 19z, for example. And of course, there's not really a topological picture. That's just a finite set, of course, like the discrete set. But if you want to draw it in any way, so here like the residue class from 1 to 18, and here from 1 to 18, I drew all the points that satisfy this equation, you get a picture like that. Probably the only thing you could see, I mean, there's still symmetry of y goes to minus y. So if y satisfies that, then minus y satisfies that, and y to minus y is coming from this or that y, of course. So that's why you have a symmetry, like along the central line. But that's probably pretty much all one could see. Like, otherwise it looks like a random collection of points, I guess, at least for now. And that's what a picture would be like there. In fact, that is useful. And so that actually, that it does look like a random collection of points is a very useful thing, because that's actually used, for example, in cryptography. So the structure of this thing is so, well, from one point of view, so complicated that whenever you do some crypto system on that, it's really hard to crack, because it looks like a random collection of points. You do that in more detail. But still, like, the construction is quite simple, so there's some way to do with these things. Just like, well, we'll see this later also in class. So maybe you've heard this keyword, like elliptic curve cryptography is like a big thing in computer science right now. It's actually used in a lot of things, and that happens to be an elliptic curve. Oh, maybe one field that I forgot. I mean, you could also consider like the rational numbers over Q. And there's just one thing to mention, I guess, like this, the famous Fermat's last theorem is actually a question about plane curves. Because if you consider this equation, x to the n plus y to the n equals 1, and ask for solutions over the rational numbers, then, I mean, you could clear the denominators. If you had a solution like that, you multiply with the denominators, you get a solution for that in integers. And that was exactly the question, whether there are solutions in integers of that equation. And the statement was no, there are no non-trivial ones, meaning other than where one of them is 0 and the other two are just equal. There are no non-trivial integer solutions. So that means even like this theorem is a special case. Of course, you need a lot about plane curves to do that, but the actual proof now, like proven by Wiles, this theorem, as you probably know, does use methods of algebraic geometry quite a lot. So you can see, like, really depending on which ground fields you have like totally different things to look at. But the theory, the starting theory at least behind it, would be pretty much the same. And that's what we do here. Maybe one. So there I think you can see already many relations, right? So like commutative algebra, as I said, is obvious topology. You saw like in the picture. Here you have like number theory, cryptography, you see all these relations. Maybe one thing about the complex analysis part. So as I said, so in case you've heard these, so what it would be like the Einführung Funktionentheorie class, like, or any kind of complex analysis class, is actually pretty much related to the complex case, of course, here. So if I just go back to the complex picture here. So for example, if you have a case like that of such a curve, one question, just one example that you could study, and we'll do something also like that in class, just with algebraic methods, as I don't want to assume complex analysis, is the question, what are nice functions on this torus? Where nice means, well, I mean, every category has its own nice functions, and in our case, for the algebraic ones, it will be essentially functions that are rational functions or quotients of polynomials. So that could be expressed in terms of polynomials in x and y. And that would be considered the functions that we allow there. In the same way as linear algebra allows linear functions and algebra allows polynomial functions. So here we'll have quotients of polynomials. Whereas, like in complex analysis, you usually allow differentiable functions, or called holomorphic functions there. And these are the nice functions to consider there. So let me not be too specific here and talk about nice functions. And you would ask, what are the global, like defined everywhere on the whole torus, global nice functions on this thing? And of course, there would be many. So if nice meant continuous, there would be many functions on that, right? On the thing. Just take anything that wobbles around here on the torus. However, if it has to be holomorphic or rational, that's quite a big restriction, actually. And so in case you know complex analysis, so maybe, did you know some complex analysis? A little bit? Then you could quite simply answer this question, because first of all, the first observation is, that doesn't need complex analysis, but just usual analysis. That's a compact space, and if you have an at least continuous function on that, it will have, at least from the absolute value of the function, or over the complex numbers, that's a continuous function, it will have a maximum minimum. So it will have a maximum and minimum, and if you then remember your complex analysis class, there was a maximum modulus theorem, maximum Prinzip, which means that there is no local maximum of a nice holomorphic curve. unless it's a constant function. And that means in the complex analysis setting, it's quite simple to prove that any, I mean, that's essentially what I told you, that any holomorphic function on such a thing is a constant. There is no non-trivial holomorphic function on that thing. And the same we'll prove in this class using entirely algebraic methods. It's actually true if you consider like quotients of polynomials that are well defined everywhere, given a nice function here, there's only the constant ones. And of course, if you prove it here, then it works over any field, not just over the complex numbers. But I mean, there's very many cases where complex analysis and algebraic geometry prove over the complex number essentially the same statement with entirely different methods. So one method is using analysis, the other is using algebra. So that's also very, very nice. And I guess, so we'll not have time to touch that here very much, but well, if you know complex analysis and we're interested in that, I mean, you've probably seen that there's also a class on Riemann surfaces this semester by Jörg Zintel offered. And that's exactly the complex analysis side. So a Riemann surface is essentially a plane curve just from an analytic point of view instead of an algebraic point of view. So that means those two classes, I mean, I would expect that there's many similar, I mean, not every theorem, but I mean, there will be some similar results in those two classes where we only do algebra and he's probably only doing analysis. So if you're interested in that, also a nice class too. Yeah, so that would be some examples and motivation, I guess, to start with. Any questions about that? What I wanted to say about before we actually start with the actual definition. Oh, great. So then let's turn and. So let's start with the actual class and introduce, like in the first chapter, the objects, or at least like the first class of objects that we want to talk about. So you can also go back to Blackboard. Well, that's the first chapter, and that is on affine curves. So affine plane algebraic curves. So there will later be projective ones. That's why we distinguish here. And for that, let's set up some notations here. So the general setup will be as follows. So first of all, as in commutative algebra, if we say ring, we always mean commutative with 1. So rings are always commutative with 1. Then we always have a fixed ground field that we always call K. So there's no assumption on that for the moment, as we've seen, like, I mean, every case is interesting in itself, like via the finite field or the rationals or the reals or the complex. So I deliberately do not want to assume from the beginning it's algebraically closed. I mean, it's very tempting to do so because many things would be nicer, but also we would exclude many interesting cases. So we just take K as any fixed ground field. So at some point in the class, we'll then restrict to the algebraically closed ones, but that will take some time. And so the main ring that we will work in, as we said, is the polynomial ring. So let me just quickly recall. So for K, and then in square brackets x1 up to xn will denote the polynomial ring in n variables over K. Meaning, of course, that the elements here are these formal sums, right? So you could write them as sum and then some coefficients a I1 up to In, x1 to the I1 up to xn to the In, where the ai an are all elements of K. You sum over I1 up to In, all natural numbers, and it's a finite sum. Right? So such formal finite sums will be our polynomials. Of course, most of the time we'll need it in two variables, and then we usually call the variables x and y, right, instead of x1 and x2. Such a polynomial, as you know, determines a value. If you have a point in k to the n, you can plug it in and you get an element of k. So, or in other words, every polynomial determines a polynomial function from k to the n to k. But as usual, the function, it's not defined as a function, so several polynomials might define the same functions if you're over finite fields. So if we call such a polynomial f, for example, then we could say for a point, say P, maybe with coordinates C1, Cn, and Kn, such a polynomial determines a value, hence is a function on k to the n, namely which we then write as f of p. I mean, as you would expect, right? It's a sum over these coefficients, and then you plug in the values for C1 up to Cn for the variables. So that we will use in a second. The properties of the polynomial ring, I guess, which is quite easy to see. I mean, it's an integral domain. The units are just the non-zero constants. Okay, and so just some basic facts, which you hopefully know is an integral domain. And the units are the constants, or the non-zero constants. And there's a degree function on that. There's a notion of degree of the polynomial. And here, unless we say otherwise, degree will always mean total degree, which means like it's the sum over all the exponents. So not degree with respect to one variable, but with respect to all the variables. Any f, at least non-zero, has a degree, which we call deg f, which is then a natural number, and it's the total degree. So i.e. in the notation above, the maximum of all occurring I1 plus In of all the exponents. And we would call a polynomial homogeneous if they all have the same exponent. So f is homogeneous of degree d if all terms have degree d. Again, in the sense of total degree. Well, these are somewhat simple properties. I mean, there's them like all one-liner to prove, I guess. And what is not so simple, which either you know it or you just have to take it for as a fact from commutative algebra, is that this is a unique factorization domain, as it's called. It's a factorial ring. And what this means is that just as, like, for example, I mean, you feel, you know it for polynomials in one variable, or like for the integers, that every non-zero non-unit has a unique decomposition in primes. And that holds for this polynomial as well, for this polynomial ring. So this is usually proven in commutative algebra. So either you just know it or you just take it on faith. It's an easy to understand statement. So let me just write this down here as a fact, a commutative algebra fact. So okay, x1, xn is, I think you either call it a factorial ring or sometimes call it the UFD, means unique factorization domain. So it pretty much means two things. So first of all, I mean, as in general, like integral domains, you know, like that prime and irreducible are different notions, and for those rings they are not. So that means first of all that prime polynomial is the same as an irreducible one. And it also means, so what actually the name stands for, like that every non-zero non-unit, so essentially every non-constant polynomial has a unique factorization into irreducible polynomials or prime polynomials, which would be the same. That's, for example, something that breaks down for other rings that are maybe of the form polynomial ring modulo some ideal, which is often considered in algebraic geometry, and that makes things a lot more complicated. So it's actually a nice situation here that we have this factor. So as I say, we just take this for granted that this exists. Of course, as usual, I mean, as already for the integers, you know, factorization is hard, you know, and it's, of course, it's also hard for polynomials. So there will probably never be really questions, do this factorization for a particular polynomial, unless it's trivial to see what problem to do that. Yeah, so this is the basic setup that we have, and with that we can use our, we can now define our affine varieties and affine curves, and what's the topic of this chapter. So let's start with the definition. The affine curves, or affine varieties first, yes, and then the curve, yeah, affine varieties first, and then curves come later. Namely, first of all, we define just the space where they live in. So for a natural number in an n, the affine n space, n-dimensional space, is defined as, so it's usually write this with A with the for the double line here, and that is defined to be, so sometimes if you want to denote the field, we just write a n over k, and that is just k to the n. And the reason why there's a different notation for that is that we mean like it's kn without all the structure you may think of. So if you usually say here's something like k to the n, you think, oh, it's a vector space. Maybe you think it's a ring or whatever field you're coming from. We don't want to regard this structure. So an will just be the set where our curves lies in, but for example, we never use a 0 point of that or anything. So that's the reason why we have different notation. So i.e. k to the n without, for example, the vector space structure or any other structure that you might think of. It's just a set for the moment. In particular, there's nothing like a 0 point or so. And I mean, there is a 0 point, but it doesn't have any special role. Now, an affine variety, first of all, so I mean, if you had a class on commutative algebra, you might have heard this term, is just in such an affine space, the zero locus of a collection of polynomials. So what we do now in the second part, so for a subset of polynomials, so call this maybe S, in x1 up to xn, we define something, I call this V of S, V because these things are then called variety. This is all the points P and AN where all the given polynomials vanish, so f of P equals 0 for all f and S. This is hence a subset of AN. This is called the zero locus or zero set of S. For obvious reasons. So it's the set of all points in the n where all the given polynomials vanish. And the case that we will essentially always have, I guess, is where the set is actually a finite set and maybe even only consists of one polynomial. And then you usually, so for a finite set, so if this is say f1 up to fk, a finite set, we write v of, and then you would have to write the set f1 up to fk, but we usually write this without the set bracket, so just as v of f1 up to fk. In particular, if we have only one, we would just write v of f, right? It just means the zero locus of f. And as I said, so the name is, so subsets of this form are called affine varieties. The form v of s are called affine varieties. So that is slightly more general than the plane curve that we want to consider. Of course, that will be then in the n equals 2 case, and for one variable, we just do that in a minute. So that's, but we will later on, when we consider not the affine but the projective ones, we'll come back to things like that with 3 variables, so that it's nicer to have this in general at the beginning. I don't know, so if you had probably commutative algebra, you probably talked about that, I guess. Right? There's one simple remark how this behaves for, so we'll, as I said, mostly be concerned with V of just one polynomial. And that is how these things behave under union and intersection. So if you take the union of 2 of these things, so read this is the 0 locus of F and this is the 0 locus of G, then this would just be the 0 locus of F times G, as a product of polynomials is 0 exactly at the point where one of the factors is 0. And it's because the values of the polynomials are in a field, and hence it can only be 0 if one of the factors is 0. And if you intersect 2 of these things, the V of F intersect V of G, then, well, I mean, there's no way to write it in that form, but by definition, it's just V of F comma G, right? It's just how we defined that. But that's usually not a curve. It would just be the intersection of 2 things. And of course, that's if these 2 are curves, like in the plane that you would intersect, you would expect this to be finitely many points, for example. Yeah. So that's in general varieties. And now, so what about plane curves? Now, of course, one would expect now to say that a plane curve is something like that, where you have n equals 2, so that means you're in the plane, and probably only one equation. And in fact, some people, some people in literature would do that. However, we don't want to do that here, because it turns out that algebraically it's nicer to do it a little different. And maybe to say that the polynomial itself is the curve. I mean, if you're coming a little bit from commutative algebra and want to translate things between geometry and algebra, I mean, then you've probably seen already that oftentimes the algebraic picture is maybe the nicer picture, and the geometry is more to visualize stuff. And hence you want this subset of ak to the n rather maybe represented by the polynomial itself that does it. So the idea would be that a plane curve should be something of the form V of F in A2 for some polynomial F and Kxy. So we call the 2 variables xy. However, it is more convenient, as we'll see in the class in many places, I guess, to not define a curve as a veritable subset without some structure in a set which doesn't have some structure, but you rather use the polynomial itself. However, algebraically, it's nicer to define a curve by its polynomial. Which will then, if we think about it that way, then we will usually use capital letters for these polynomials. I mean, they are still polynomials, but if we think of them as curves, we will denote polynomials by capital letters if you want to think about them this way. So to think about them as curves. And there's one thing that we can mod out from the beginning, namely it's clear that a polynomial and a polynomial times a unit, so times a non-zero constant, would have the same zero locus. I mean, you can multiply a polynomial with a constant and it doesn't change the thing. And so that we incorporate in the definition, but that's pretty much the only thing that we incorporate in that. And polynomials that differ by a unit, by multiplication with the unit, I should say. Should be the same as curves. And that's the idea that we have for our definition of plane curves. And so that means a plane curve for us will just be a polynomial in two variables over a given ground field, modulo multiplicative scalars. And in order to rule out trivial things, we want it to be a non-constant polynomial, because otherwise you just have either like the whole set or the empty set, and we don't want that. So that means it should be a non-constant polynomial modulo scalars. And that's our definition of a plane curve. But the idea, of course, in mind is that. So hence our definition. And this is now plane curves. Okay. So a plane, or I could say also a plane algebraic affine curve. But we probably always skip that and just call this a curve. Is a polynomial, a non-constant polynomial. That we then usually call denote by a capital letter, so f in kxy modulo the equivalence relation, that is multiplication by scalars, or modulo units, right? So that means f is equivalent to f prime if and only if f is lambda f prime for some lambda in k without 0. And then, of course, this v of f exists in A2, and we just call this the set of points of the curve. That is a curve. And v of f, so that means the set of all points in A2 such that f of p is 0 is called the set of points of f. So as I said, this is sort of non-standard. So if you look in textbooks, then I guess in many books they would define a curve just to be a subset of this form. But this is really nicer from an algebraic point of view. So you'll see this, as I said, in many places. One, for example, is that notions of being irreducible or multiplicities and components are just very easily defined on polynomials. And let's just start with that. Namely, saying that, so what's the next B part here? Yeah, of course, such a polynomial has a degree. And we just call this the degree of the curve. I mean, it's the same as for polynomials, and obviously that's independent of this, I mean, of the representative here, right? Multiplication with constants doesn't change the degree. So say the degree of a curve f is defined as its degree as a polynomial and there's also special words for this curve if the degrees are low numbers. So for example, special names. If the degree of f is 1, we call this a line for obvious reasons. If the degree is 2, there's actually two names for that. One either calls it the quadric or a conic. That's the same thing. It's pretty much used interchangeably in literature. And for 3, you would call it a cubic. And then, I mean, there's obvious coming words with like quartic and quintic and so on. And that's, for example, that's already an example of the case that this is very easy to define if a curve is just a polynomial. Right? If a curve was a subset of A2, we would have a much harder time to define what its degree should be. And we would finally, at the end, also arrive at such a definition, but it's really a lot simpler in that case. With that to finish. Also, something like a decomposition into components is sort of simple for a curve because the curve is just a polynomial and the polynomial is a U of D. So that means such a curve does have a unique decomposition into components. And we also call these the components of the curve, or the irreducible components of the curve, or just components. So if a curve F has the irreducible decomposition or prime decomposition as a polynomial, so F is, say, F1 to the A1 up to Fk to the Ak, where all the F's are different and the exponents just are the multiplicity, so Fi not equal to Fj for all I not equal to j. As such an irreducible decomposition as a polynomial, we also call this the irreducible decomposition as a curve, and we'll call the Fi the components and the Ai their multiplicities in the curve. And so it's just, I mean, we just replaced polynomial by curve. We will call F1 up to Fk the irreducible components, or often we just say components without irreducible of the curve. And A1 up to Ak their multiplicities. Correspondingly, we call a curve irreducible if the polynomial is irreducible, and reducible otherwise. F is called irreducible as a curve if it is as a polynomial. And reducible otherwise. And the last thing, which is, well, we could also do this on polynomials, but maybe it's not such a common notation, is that we call it reduced if all the multiplicities are 1. Then it needn't be irreducible, but none of the factors occurs with higher multiplicity. The F is called reduced if all multiplicities are 1. And so in a sense, this definition is sort of trivial because we carry over everything we can define for polynomials just to curves, right? Because a curve is a polynomial up to units, and the units obviously don't change any of these properties. Yeah. And of course, one of the things we should study like first, and we will study in this chapter, is, I mean, the actual, as I said, like the naive way to define a curve would just be a set of this form V of f, that we want to figure out in what sense does actually V of f determine f. Right? So is it like, if we know the set of points of the curve, do we know the curve? Because usually if we want to draw pictures, if we draw pictures, for example, as we did in this motivational part at the beginning, we draw pictures. I mean, in that notation, we would say we've just drawn pictures of the set of points of these things. And so, of course, we'll want to continue to do that. And so then the question, of course, would be if the picture actually adequately represents the curve or not. But we'll do this in a minute. The first thing, I guess, that I want to give you some examples, I guess. Yeah, oh, this is a remark, I can give you that, yeah. So I guess I said this already, so often in the literature, a curve will actually be the v of f and not the f itself. You just have to look at the corresponding course where you're looking at what the definition is. A so often also v of f as above is called a plane curve in the literature. And secondly, I think we've said this already, that all these definitions are actually well defined, and because the equivalence relation up there is sort of trivial, and neither like the degree nor the components change under that. So this will be the case with all the stuff that we are doing, and I'm not always mentioning that. So, I mean, all the constructions that we did up there above are well defined, i.e. do not change under this equivalence relation. So f goes to lambda f with lambda a non-zero constant. Actually, the point, if you compare this now, it's just for those people in who've been in a commutative algebra class. Then you've probably done things like the Nullstellensatz or something. So you know that there's like the polynomials or the ideal corresponding to the set. I mean, there's a one-to-one correspondence. That is sort of included in that here. However, we are doing like a little more. I guess we are pushing further than the commutative algebra class because in the commutative algebra class, the Nullstellensatz will only give you radical ideals, which sort of corresponds to reduced polynomials. And we'll extend this to arbitrary polynomials. So that means if we could just do this in examples. So if we start with the simplest possible thing, for example, say x plus y, obviously a line in our notation. So not the equation equals 0 or the set is a line, but this polynomial is a line. And its set of points, A over R, is, of course, what you would expect, right? It's that thing here. And we will use towards that line, the diagonal line, and we'll continue to draw pictures like that, obviously. So this one here. If we consider something like x plus y squared, then this would be a conic or a quadric. It is a curve of degree 2, but it has the same set of points. And that is something that already, like in the notion of the Nullstellensatz from commutative algebra, you wouldn't see, right? Because you restrict to radical ideals. And you wouldn't allow this ideal generated by x plus y because it's not radical. You would just restrict to that one. So we want actually any polynomial. And that corresponds to having something like this picture, but with a multiplicity of 2 attached to that thing. So there is a notion even in algebraic geometry that's called schemes, in case you've heard about that, which encaptures that sort of. So the idea there is to try to generalize the Nullstellensatz from radical ideals to geometric objects to have any ideals and then also some geometric objects. And we're doing already part of that here, sort of, in this nice baby case of plane curves. So there are multiplicities attached to that. So this is no longer a line. So this is a conic. It's a reducible conic and non-reduced conic with the same set of points. So that means if we wanted to draw a picture of that, it would look exactly the same. We could just maybe note a little 2 or so at the line to say it's a multiplicity 2. It's like a double line. Might want to call it double line. But it's important to note that in our definition, it's really a different curve, even if the picture looks the same. Well, to repeat one of the examples that we had in the motivation part, if I have something like x times y, where the picture is just like this, the two axes, then xy is also a conic, a reducible conic, but reduced. With irreducible components x and y. So that means in that picture, so x, like the zero locus of x would be this, that's where x is 0, and that's where y is 0. Maybe looks strange this way, but it's just, I mean, that's the zero locus of x, that's the zero locus of y, and the whole thing together would be the zero locus set of points of x times y. Let's take this other, like this cubic curve again. So we had this example of y squared plus x minus x cubed, which where the picture was this. I have this on the slides next, if you remember, over the reals, for example. Of course, you have to fix the ground field always over R. Is now, for example, I said this already, like when we had the pictures, is actually an irreducible curve. I mean, if you look at the picture, you might think it's two components, but really have to be careful with the word component now, because that thing itself is not an algebraic curve. You have to take both together. And you could see this quite easily because, I mean, this is a cubic curve. And if that fact, I mean, if a polynomial would factor into two factors, then the degrees into two non-constant factors, then the degrees must be 1 and 2. But if you had a factor of degree 1, this would contain a line, and it just doesn't on the picture. So that is an irreducible polynomial. So that is an irreducible curve, although it maybe doesn't look like one. So I gave you sort of like an intuitive argument, like the thing, it would have to contain a line, and if you see the picture, it doesn't look like that. But you could also prove this algebraically, like that this is an irreducible polynomial. Let's not do that here. Maybe you could do this as an exercise if you like, but we don't have to do that here. And even other cases, for like if you take d over the reals, over R, if you take something like x squared plus y squared plus 1, then the zero locus of that is just empty, right? I mean, there's no real number satisfying that. So this means this would have an empty set of points, but still it's a totally valid conic, right? I mean, it's a curve. And that's again something where, like from the Nullstellen that you maybe know from commutative algebra. So first of all, we restrict to algebraically closed, which we don't do here. And then you don't have this, I mean, you don't see these phenomena here. So in our case here, this would be, so this is a conic curve, although it's set of points, so I call this f, although v of f is empty. And another thing along these lines would be if you take x squared plus 2 squared plus 2, it's still a conic curve with empty zero locus, but it's a different curve. So there's two different curves. I mean, it's different polynomials up to scalars, but if you try to draw it, you just get the empty set. Okay? So it is a different curve. Call this G. With V of V is empty. Right, and so if we see these pictures, of course, then I guess the natural question would be, I mean, in what sense, if we just draw, I mean, usually when we draw pictures, we draw V of F, but here we see in these pictures, I mean, this doesn't determine at all the F or G, and you just draw an empty set. So in which cases, or in what sense, is it actually useful to draw V of f? So in which cases can you recover f if we know V of f? And so that would be like the one and last question that we actually want to study. So to have some results actually in this first section and not just definitions, would be in what cases, in what sense does V of f actually determine back f? And that goes now into the direction of the question now is in what cases does V of f, so the set of points, determine back f? So that if we draw a picture, we do a sensible way of drawing this thing. And so for that, we need to, so we've seen already two cases in which case this goes wrong, namely in these examples. So first of all, these multiplicities here cannot be seen in the picture, right? Unless you know the component with multiplicity. So if we have a non-reduced curve, then we don't see the multiplicities in the set theoretic picture. So there's two problems. And that's first of all, I mean components, or say multiplicities of f in the case of non-reduced curve cannot be seen in the picture, cannot be seen in V of f. And the second thing is like the last here, if we have a field which is, from the problem here, of course, which is not algebraically closed, then it might be that the zero locus is just empty, although we have a non-trivial curve. So V of f might be empty. Or some f, well, if there are polynomials without zeros, there are non-constant polynomials without zeros. And so, of course, it doesn't determine back f. And we will see now, so from our language here, now I would say that these are the two main points that make problems. And if we somehow can exclude them, then it works. So if you compare it to the Nullstellensatz, you would see like the first thing somehow corresponds to the case that you only consider radical ideals, right? So you don't allow multiplicities in your idea, in your polynomials. And this corresponds to that you want to have an algebraically closed field. And so let's actually start with that one. So the notion of an algebraically closed field is clearly important here as well. So, so to study this, we need two things actually. So first of all is the notion of algebraically closed field. So I guess you all know that, I guess, or do you, right? An algebraically closed field. So it's just a, so defined, it's only by polynomials in one variable. That namely every non-constant polynomial has a zero. And that will clearly play a role, because if we have such a case, then we'll see that this, like what we have in D, cannot happen. So first of all, it means just a remark, and I can just do this quickly. So K is called algebraically closed if every non-constant polynomial has a zero. In one variable, so one variable has a zero. And this is the case, for example, for the complex numbers, but you probably then also know that every field can be embedded in an algebraically closed one. Maybe you've seen this somewhere, either in algebra and commutative algebra, that it's true. So in the same way as like R sits in C, or Q sits in C also, like finite field or any other field you could write down sits in an algebraically closed one. So that usually, that's also why many people would restrict to algebraically closed fields, because you say you can always pass to an extension field and then do the algebraic geometry there, but you still sort of lose the geometry, so we don't want to do this here. But we'll clearly need this notation, so it's called algebraically closed if that. And well, I mean, one thing, of course, so note any algebraically closed field is clearly infinite. You probably know this then as well, right? Because if it was a finite field, like it has elements C1 up to Cn, you could form the polynomial x minus C1 in the product and add 1, and then it would be a polynomial without a 0. So that means any such algebraically closed field is in fact infinite. If you know this notation. We'll need this in a minute, and that will ensure that something like that in D does not happen. And there's one more construction that we'll need, and that is that of a quotient field. And so if you have an integral domain, you can form its quotient field. So you've probably seen this then as well. Just write something down. So if R is an integral domain, we can form the quotient field, or sometimes it's called like field of fractions. And I'll denote this by quad R here, and that's the element of these forms their quotients, F over G, where F and G are in the ring, and G is not equal to 0. This notation, the quotient, is just a notion for an equivalence class, namely an equivalence class of pairs F comma G, where the equivalence class is exactly the one that you have, that you expect for fractions, namely that F over G and F prime over G prime are the same if F G prime is F prime G. And it's then easy to check that this forms a field, and that's called the quotient field of fractions, where F over G is the equivalence class of pairs Fg modulo Fg is equivalent F prime G prime if and only if Fg prime is F prime G. So the standard example that you all know is if you do this to Z, you get Q. Right? That's the way to get the rational numbers from the integers. For Z is Q. However, the most important example for us will be to apply this to a polynomial ring. I don't know if you've seen that before. If you do this, you get a field of rational functions, as it's usually called. So essentially you take, in the same way as you would call a rational function in school, like it's a quotient of polynomials. So if you have quad k and then x1 up to xn, then the standard notation for that is k with round brackets x1 up to xn, like this. And well, this then consists, of course, as the definition says, of all these f over g, was the same as before, where f and g are polynomials. And so it's usually called the field of rational functions in n variables. Although, of course, it's sort of confusing because as for polynomials, it is actually not defined as functions, right? I mean, it's the formal algebraic construction here. And of course, the same as what you could have for polynomials over finite fields, that different polynomials determine the same function. Of course, you could have that different elements of this thing determine the same function. Also, they are not even functions on all of k to the n because you might have something in the denominator. So it's pretty much just a name for that thing. But that is essentially the most important case that we will consider here in class. So this case is not that important here, but we work with the polynomial ring and the quotient field of the polynomial ring is somehow the important thing that we'll need. Yeah, so these are the two ingredients that we need, and then we can start proving something. In the direction of in what sense this v of f determines spec f, in which cases. And so our first small lemma is just about how big these sets actually are. So if we are over infinite or even algebraically closed fields, then the statement is, and that's our first lemma. So for that, say we let f, capital F, be a curve. So of course, like meaning affine plane algebraic curve over some field. We don't assume anything here for the moment, and of course, by definition, it's just a polynomial essentially. Then the first statement is, so there's two statements. Namely, if k is algebraically closed, then v of f is actually infinite. Then v of f infinite. So recall we had, I hope I said this, I don't in the definition, so we wanted a curve to be a non-constant polynomial. Did I say it? I hope so, right? So of course that excludes these things that we have empty sets here. So that means the thing that we had in the last case with the x squared plus y squared plus 1 over the real cannot happen over algebraically closed fields. We never have empty zero loci, and even we have an infinite zero locus even. What? Degree what? Curve? No, curve is anything. A conic is degree 2 polynomial. What? Oh, in two variables. I mean, yeah, into, oh, that's what degree is to. Yeah, it's always in, that's a curve. I mean, a curve for us always means a polynomial in two variables. Yeah, so i.e. f is in k, x, y, non-constant modulo scalars. That was our modulo units. Eh? That was our definition. Yeah. So curve is always, I mean, curve somehow means one-dimensional, and that's a zero locus of one function. So curve always means plane, algebraic curve in that sense. One polynomial, two variables in the whole class. I mean, it has some plane algebraic curves, not in algebraic geometry. Right? Yeah, right, no problem. That's what I'm saying. Right, and B, well, if K is at least infinite, which is a weaker statement, of course, then the complement is infinite. So if you take A2 without the zero locus of F, then this is infinite. So it means in the algebraically closed case, both the set of points and its complement will be infinite sets, particular not empty. And if we have at least an infinite field, then the second one holds. So let's just prove that, and it's probably the last thing we can do today. And we can actually start with both cases simultaneously. I mean, so assume, so F is a curve, and it's supposed to be non-constant, and so that means it contains at least one term that has an x or an y. And so if we now consider for this proof here the degrees separately, we can assume that the degree with respect to x or y, at least one of them is positive. So as F is non-constant, it has a positive degree with respect to at least one of the variables and say this is x, And so then we can write f as a polynomial in x, then the an x to the n plus and so on a1x plus a0, where now the ai are polynomials in y, and n is greater than 0, and the an is not equal to 0. So it means where n is a natural number but not 0, so it's a non-constant polynomial. The ai are all polynomials in y in the other variable, and the an is not equal to 0. That we can do either in this for this variable or the other or both. In particular, that means that this an is a non-zero and non-constant. It's a non-zero polynomial in y. And so this means that it has at most finitely many zeros. And in both cases, the field is infinite. And that means there's infinitely many values for y for whom this an of y is non-zero. So then an is a non-zero polynomial in y. And so it has finitely many zeros. Maybe none, but it has finitely many. And this means as k is in any case infinite, in both cases, a and b, it's infinite. This means that it will be non-zero, so an of y is non-zero for infinitely many y. And for those infinitely many y, we just plug them in and consider it as an equation in x. And then it is a polynomial of degree n, because the leading coefficient is non-zero. And hence, in particular, it's a non-constant polynomial in x. And then the statement pretty much follows, because it's a non-constant polynomial in x. So if k is algebraically closed, then there will be an x satisfying that. And we will get at least one x for these infinitely many y. So we have infinitely many points. And in any case, there's only finitely many x satisfying that. And if the field is infinite, this means there's infinitely many, in particular, at least one x not satisfying that for those infinitely many y. And so that means we have infinitely many points not lying on this curve. So let's just write this down, and then we're pretty much finished. So that means f of x, so we first consider this as a variable, and then we plug in this value of y. So for infinitely many y is a non-constant polynomial in x. And that means now case A, if k is algebraically closed, it has a 0 for all these infinitely many y. And so this means we have f is infinite. And B, if k is infinite, well, it has a non-zero. There's only finitely many 0, and hence also a non-zero. And this means that A2 without VFF is infinite. The locus is completely empty if we are in an algebraically closed. And then, so that's, I guess, for today, like 3:15, yeah. So let's stop here, and then next week we'll continue here and have pretty much a statement that then goes back into the direction of the Nullstellen, that over an algebraically closed field, there will then be a one-to-one correspondence between those pictures V of f and f, as long as you attach a multiplicity to each irreducible component. Right? Then it works again. But also in the infinite case, you can say something. So that means like over the reals or something. Yeah. so that's for today. So if there's any more questions, great. So then we'll stop here and we'll see you then next week. Right?